In this video, I'm going to write these two equations in terms of the scalar and vector potentials. These guys are actually two of Maxwell's equations, and they're special because they are inhomogeneous equations. And the term inhomogeneous means that these guys have source terms. So if these equations were homogeneous, the source terms would disappear and we would just have zero. The way I've written these equations has all of the stuff involving the electric and magnetic fields on the left-hand side and all of the stuff involving the source terms on the right-hand side. So rho is the charge density and J is the current density. This is a scalar quantity and this is a vector quantity. So everything on the right-hand side is a source term. In the previous few videos in the electromagnetism playlist, I actually discussed the other pair of Maxwell's equations. And those guys were the homogeneous equations, because they had everything on the left-hand side, which involves the electric and magnetic fields, and that was just set equal to zero. There were no source terms. So rho and J did not appear in those two equations. But these guys are the inhomogeneous equations, so they do have source terms. So that is what makes these guys very important. So what we're going to be doing in this video is we're going to be substituting these definitions for the magnetic and electric field into these two equations. So this first one is commonly called Gauss's law for electric fields, and this is Ampere's law with Maxwell's modification. So this term over here is actually sometimes known as the displacement current, and it was added by Maxwell. So Ampere noticed the original law, and then Maxwell modified it and made it more complete. So this is a more complicated Maxwell equation. So we're going to be starting with this one, and then we'll move onto this one towards the end of the video. So what I want to do is I want to substitute this expression for the electric field into Gauss's law for electric fields. And then we'll do the same for this expression, but we'll also substitute the magnetic field. So let's get started. First, I'm going to have the divergence. And the divergence is going to be acting on all of this stuff over here. So I'm just going to replace the electric field with this. So we're going to have the gradient of the potential. This is the scalar potential phi, the electric potential. And I'm going to subtract from that the partial time derivative of the vector potential A. So keep in mind that we always have to add vectors to vectors and scalars to scalars. Over here, the gradient of a scalar gives a vector, and the time derivative of a vector also gives a vector. So we're adding a vector to a vector, and that's giving us another vector. If you look at these two over here, this is a scalar. The divergence of a vector is a scalar quantity, and over here we have a scalar field. So rho is a scalar field. It tells you the charge density at every point in space and time. What about over here? The curl of a vector, that gives a vector. Over here we have the time derivative of a vector times a scalar, which is 1 over c squared. This is also a vector. And on this side, we have a vector being scaled up by a scalar. So we're adding a vector quantity to another vector quantity on this side, and that's giving us a vector quantity. So this equation just has vectors, and this equation just has scalars. Now what we're doing over here is we're actually substituting this vector quantity into the brackets over here. So we'll close this bracket, and then we're going to take the divergence, and if we take the divergence of a vector quantity, that's going to give us a scalar. And we're going to set this equal to this scalar quantity over here. So first, I want to expand this out a little bit. I want to distribute the divergence operator onto each of these terms. I want you to notice this combination over here. When I act with the divergence operator onto this gradient, I'm going to have the divergence of the gradient. And the divergence of the gradient is called the Laplacian. So that's the Laplacian operator. So that's just taking the second derivatives and then adding them together. So that is what the divergence of the gradient is going to give us. So I'll write that over here. We're still going to have this minus sign. So we're going to have minus, and the notation for the Laplacian I'm going to use is nabla with a little 2 up here. So this is sometimes called the del operator, or nabla, and if we put a superscript 2, like a square, that is going to denote the Laplacian. There are other notations for the Laplacian. Sometimes you just put a delta for the Laplacian, and some people like to write it out in full. They like to write divergence of the gradient. All of those are equivalent. They're just notations for the Laplacian. So we have the Laplacian of phi. And we're taking the Laplacian of a scalar field. This is the electric scalar potential. Now, let's have a look at this second term. We're still going to have a minus sign. So this minus sign is still going to be there. This divergence we can take in over here. And what can we do with the divergence? Well, notice the divergence consists of partial derivatives with respect to spatial coordinates, with respect to x, y, and z, if we're dealing in Cartesian coordinates. And we can swap partial derivatives that are spatial derivatives with a time derivative. That's okay. That is commutative. So we can swap the order of those derivatives, and that allows us to move this divergence operator inside the time derivative. So that's going to give us this. We're going to have minus the partial derivative with respect to time of the divergence of A, and that is the second term. So you can see what I've done over here. I've just moved the divergence operator inside the time derivative. So it doesn't matter if you differentiate with respect to time first and then with respect to the spatial derivatives, or if you differentiate with respect to the spatial derivatives and then with respect to time. Notice how this is a scalar quantity and this is a scalar quantity. So we just have a scalar and a scalar. So this is actually going to allow us to conclude that, so this we can just set equal to rho over epsilon naught, right? Because this is equivalent to the electric field. We've just substituted in here. So this is what we've got. But what I'm going to do now is I'm going to multiply both sides of the equation by -1. And that's going to give me this expression, which I'll squeeze in over here. So I'm going to put this over here. And what I'm going to get is I'm going to get the Laplacian of phi plus the partial derivative with respect to time of the divergence of A is equal to minus rho on epsilon naught. And that is our first equation. And you can see that it is a second order differential equation. So what we've done is we've transformed this equation over here, which is Gauss's law for electric fields, and we've turned it into this equation, which involves the scalar and vector potentials. And it also involves the source term that involves rho. So I'm going to do an analogous derivation for Ampere's law with Maxwell's modification. So the Ampère-Maxwell law. So I'm going to do that in red, so we match this color. And then we'll see that we're going to get two very important equations. And in the next few videos, we're going to manipulate those equations, simplify them, and make them easier to solve. So let's substitute the magnetic field over here and the electric field over here. We're going to do that underneath. So if we substitute the magnetic field, we're going to get the curl of A. So that's going to give us the curl of the curl of A. So we're taking the curl twice, and we're allowed to do that. Sometimes you're not allowed to apply a differential operator twice. For the divergence, if you take the divergence, taking the divergence of a vector quantity is going to give you a scalar. And then if you want to apply the divergence to that again, you're going to run into trouble. But for the curl, we're actually going to use a very useful vector identity. And this is a well-defined quantity. Whereas taking the divergence of the divergence, you're going to run into trouble for that kind of scenario. So this over here, this is the first term. We've just substituted this definition of the magnetic field in terms of the vector potential. Now let's substitute this part over here. So I'm going to have minus 1 over c squared. That's this scalar coefficient over here. And then I'm going to have the partial derivative with respect to time of the electric field. And the electric field is just over here. That's the same thing that we substituted up over here. So we're going to have minus the gradient of phi minus the derivative with respect to time of A. And that's a partial derivative. So this is what we have on the left-hand side. So what is that going to equal? I'm going to set that equal to, well, this guy over here, I'm going to use a useful vector identity. The curl of some vector field A can be written as the gradient of the divergence of A minus the Laplacian of A. Now, keep in mind that this is not exactly the same Laplacian as we have up here. This is a vector quantity and this is a scalar quantity. So there's a slight nuance. This is not exactly the same operation because here we're implicitly looking at three separate equations. We have a x, a y, and a z. So that is what we're trying to describe over here. So this is the vector Laplacian. So this combination over here, the gradient of the divergence minus the Laplacian, that is equivalent to the curl of the curve. And that is a vector identity, which I'm not going to prove in this video. Now let's have a look at this term over here. We can expand it and we can get two additional terms. So we can see that there's a minus sign and a bunch of minus signs over here. These minus signs are all going to cancel each other out. You have minus and a minus, that's going to give us a plus. So what can we do with this first term over here? We have a time derivative, and then we have a gradient. Now the gradient is going to have spatial derivatives, just like the divergence. There's going to be derivatives with respect to x, y, and z if we're dealing with Cartesian coordinates. So what we can do is we can swap the order of these guys. And we can also bring in this constant, right? Because this is just a scalar. You can bring it in inside the operator. So what is that going to give us? Well, that's going to give us plus the gradient of 1 over c squared d phi dt. So that is this first term over here. So we're going to have the gradient acting on all of this stuff over here. So we just swap the order of these guys. And we're allowed to do that because these partial derivatives are commutative. Now let's have a look at this term over here. This term has one partial derivative with respect to time. And what we're going to do is we're going to differentiate again with respect to time. So we're going to have a second derivative. And we're also going to lose the minus sign because we have a minus sign over here. So that's going to give us plus 1 on c squared. And we're going to have a second derivative with respect to time. And now what we're going to have to do is we're going to have to rearrange these guys a little bit. So we're going to rearrange them, and we're also going to identify some similarities. We're going to group this guy and this guy together, and we're also going to group this guy and this guy together. Can you see that both of these terms have a gradient operator? There's a gradient operator acting on this and a gradient operator acting on this. So we can use distributivity, and we can group those terms together. And that's actually what I'm going to do over here underneath. So I'm going to take the gradient of both of these guys, just the sum of these guys. And that comes from distributivity. So I'm going to have the divergence of A plus 1 over c squared. And we're going to have this partial derivative with respect to time of phi. And I'm going to close the bracket over here. So that's everything that the gradient operator is acting on. This combination over here is actually going to become very important in the next few videos. This is going to be linked to the Lorentz gauge. And if we set this equal to 0, that is the condition that is imposed by the Lorentz gauge. And we'll get to that in the next video. So we've taken care of this term, and we've taken care of this term. Now, let's have a look at these two terms over here. So what we're going to get is minus the Laplacian of A plus 1 over c squared. So that's this term over here. And we're going to have this second derivative with respect to time. And one important thing I want to stress about this is that you have a Laplacian, and this is actually telling you that you have spatial derivatives. And these are second order spatial derivatives. So you can combine this together into a single operator. And that is called the D'Alembert operator, or sometimes it's called the D'Alembertian. So it's a bit of a difficult word to pronounce, but this is the D'Alembert operator. We can group that together. And what I'm also going to do is I'm just going to set this equal to the source term, right? Because we know this is equal to the left-hand side. So I'm just going to set that equal to mu naught. And I'm going to have j over here. And now, just as I did up here, I'm going to multiply both sides by minus 1. And that's going to give me this expression down here. Dual arrow. So this over here is going to get negated. So I'll put that onto the right-hand side. And this over here is also going to get negated. We're going to move this minus sign over to this term. So what is that going to do? That's going to give us this over here. We're going to have the Laplacian of A minus 1 on c squared times the second derivative of A with respect to time. And this is a partial derivative. And so this is going to be equivalent to the D'Alembert operator acting on A. And then we're going to have to subtract from that the gradient of all of this stuff over here. So I'm going to write the gradient of the divergence of A plus 1 on c squared times just the first derivative of phi with respect to time. And this is a partial derivative. And this is going to be equal to minus mu naught j. So the reason I've chosen to multiply those signs by -1 is to keep it in this form. What I want is this combination to have a positive term over here and a negative term over here. Because the definition for the D'Alembert operator that I'm going to use is going to have positive values for the spatial derivatives and a negative value for the time derivative. Now there's actually some freedom in what we can choose over here. Is because there's a thing called the signature of the metric in special relativity. And this ties very closely to special relativity. The Lorentz gauge is very good for working with relativistic electrodynamics. So what you can actually do is you can swap the sign convention. You can choose time to have the minus sign and the spatial coordinates to have plus signs, or you can choose the plus sign to be associated with the time derivatives and all the temporal components, and then you're going to have minus signs for all the spatial components. So as long as they have opposite sign, then you're actually going to be good. So you just need to have opposite signs for the spatial and temporal components. But the convention that I'm going to use is going to have plus signs for this Laplacian and a minus sign for this second order time derivative. And that's also going to be in the next few videos as well. So the thing that I'm going to write is actually I'm going to condense this down. I'm going to write all of this stuff over here in a different form, in a shorthand notation. All of this, I'm just going to write a big square box. And that is the same as the D'Alembert operator. So this square box is sometimes written with a little 2 over here. So I'll put that in just for consistency. We can write a little 2. I think in some of the previous videos in the electromagnetism playlist, I omitted the 2, but I mentioned that there are multiple notations that are equivalent. So some people like to put the 2, some people like to omit the 2. So what we have is the D'Alembert operator minus the gradient of this term over here. So we have the divergence of A plus 1 on c squared times the time derivative of phi, and that's equal to minus mu naught j. So we actually have pretty similar expressions. Over here, we have an expression that involves phi and A, and we have a source term with a minus sign. And down here, we have a source term with a minus sign as well, but now we have this slightly more complicated expression, though it involves A and phi. So this looks a lot less intuitive than Maxwell's equations. Maxwell's equations have a pretty good physical intuition. Divergence tells you how things are coming out, and curl tells you how things are circulating in 3D space. So when you have operators like divergence and curl, and you have physical quantities like the electric and magnetic field, it's a very intuitive way of describing it. But what I'm trying to present over here is an alternative way to look at electrodynamics. I'm writing all of the information that's encoded in Maxwell's equations in these second order partial differential equations. So this one over here and this one over here. And this is what we're going to use in the next few videos when we look at different choices of gauge. So we're going to have a look at the Lorentz gauge, and the Lorentz gauge is going to get rid of all of this. And I'm also going to have a look at the Coulomb gauge, and the Coulomb gauge is going to have this term disappear. And that's going to give us some simplifications that allow us to solve for the scalar and vector potentials more easily. So a big summary of what we actually managed to do. We have taken the inhomogeneous pair of Maxwell's equations. We've substituted the definitions of the electric and magnetic field, which we derived in a previous video. And these definitions are written in terms of the vector potential and the scalar potential. After substituting and doing some algebraic manipulation, we managed to get 2 second-order differential equations. So now we have 2 second-order differential equations instead of Maxwell's equations, which are 4 first-order equations. Right? These guys over here just have first-order derivatives. You're just applying divergence once. You're just applying curl once. You're just taking time derivatives once. But in these equations, you're having to do multiple differentiations. See over here, the D'Alembert operator, that's a second-order operator. This over here, we're taking gradients of divergence. We're taking the gradients of time derivatives. And over here, we're taking time derivatives of a divergence, and we're also taking Laplacians. So those are second-order operators. One final thing I want to say is that these guys over here are all scalar quantities. So you're adding scalars to scalars, and that's giving you a scalar field. So rho is a scalar field. Whereas over here, we're adding vectors to vectors. This is a vector field over here. This is giving us a vector quantity, and this over here, we're starting off with a scalar quantity inside the brackets, right? This is a scalar, divergence is a scalar, this is a derivative of a scalar field. So we're taking a scalar and we're turning it into a vector by applying the gradient operator. And then we're adding a vector to a vector to give us another vector. So we're going to use these two equations in the next few videos. Make sure you watch those videos. They're all in the electromagnetism playlist.